Alright, so in this particular video, we have some guys pulling a box up a ramp. The ramp is inclined at 20 degrees to the floor. So in this diagram here is the angle of the ramp relative to the floor, which is 20 degrees. It says the rope pulling up the box is at an angle of 30 to the ramp. So here is the force that's being applied by the person, but the angle relative to the ramp is 30 degrees. So right away you notice here we have two different angles that we need to be careful with, okay? It says if the mass of the box is 50 kilograms and the tension in the rope is 240 newtons, it wants us, one, to determine the magnitude of the acceleration of the box as it's being pulled up, and B, determine the magnitude of the contact force F of N that's exerted by the ramp onto the box. Excuse me. So, alright, let's go and crack this out. As usual, it's important to draw our forces out so that one, we don't forget anything, two, we know what to consider as we set up Newton's laws of motion for these types of ramp problem. Okay, here, the purple arrow, this is my weight, F of G is pointing down the page, and then this is F of G Y. That's theta. This theta here is the same as the theta of the ramp, which is 20 degrees, not the 30 degrees. Okay, so this angle here is always going to be the same angle as the ramp. Okay. This component F of Gy is mg cosine theta. It's cosine because, once again, relative to this angle touching the weight, it is the adjacent leg, and adjacent is cosine in mathematics. Here, the other component of F of G is F of Gx, and F of G is our sine because relative to this particular angle, it is opposite. So therefore, it's mg sine theta, sine being opposite over hypotenuse. And our hypotenuse in this case would be F of G, because F of G now lies in between the X and Y axis. Once again, if you haven't seen the first 3 videos, I highly encourage you to do so. The X axis is now the surface of the ramp. Watch when my cursor is going back and forth. So the surface of the ramp is now our X axis, and therefore the Y axis is perpendicular to the surface of the ramp, which is now this line, not up and down the page as your normal X, Y coordinate. Alright. I'm also going to go ahead and identify the f of x component for the f that's being applied by the person. Once again, the x-axis is along the ramp, so this is fx. Relative to this angle 30 degrees, this is f cosine theta, because this is your adjacent leg of this particular applied force. And then last but not least, the opposite leg would be f sine of theta. Once again, I do want to point out that we have an angle of 20 degrees and an angle of 30 degrees, so it's important that you pay attention to which theta to plug in based on the component that you're applying. Alright. In order to find AX, let's go ahead and set up Newton's second law in the x direction. Net force in the x direction is go to MAX. Here in this case, the only two components that I see along the surface of the ramp is F of X, which is pulling the crate or the box here up the slope. But at the same time, I have F of Gx here that's pointing down slope. Once again, F of Gx is always going to be pointing down slope, whether you're pushing down or up. So this particular component, F of Gx, is pretty easy to keep track of, okay? Therefore, I want to set up Fx minus F of Gx. Once again, Fx is pointing up the ramp, F of Gx is pointing down the ramp, so I subtract those two vector components. F is F cosine theta, and then F of Gx is mg sine theta, which is going to MAX. But here, F is 240. Cosine of this particular force that's being applied is 30 degrees. So it's important that you plug in the right angle here and not get messed up or not get mixed up with the angles. Here, this is cosine of 30. The mass here is 50 kilograms, and then 9.8 for G. Again, once again, the negative sign is already taken care of, so plug in positive 9.8 here. Sine what of theta, but what's the theta? Theta is 20 degrees because F of Gx is referencing this angle of the ramp, which is 20 degrees in the diagram. And our mass here is 50 kilograms on the right. Simplifying the left hand side will give us about 207.85 minus 167.6, which is equal to 50 AX. And we take the difference on the left side and at the same time divide both sides by 50 in order to solve for AX. We should get 40.25 newtons divided by 50 kilograms, and our AX is going to come out to be about 0.81 meters per second square. And it says for magnitude, so I don't really care for the direction. So let's do part B. Part B asks us to find the magnitude of the normal force. Well, in order to find the normal force, we need to recognize that the normal force is along the y-axis, which is once again tilted for these types of ramp problem. Here I've drawn f of n slightly smaller than f of gy as compared to previous example problems, because in this particular problem we have an f that's being applied by the person here, which already has an f of y component. So in this diagram, I noticed right away that we only have one y component pointing down the ramp, but at the same time we have two forces that are pointing up. So here is the force exerted by the ramp onto the box, which is Fn. At the same time, based on how the person is pulling the box, there is a f of y contributing to that. Okay, so we have two arrows pointing up along the y-axis and then one arrow pointing down the y-axis. So I'm just going to expand that. I'm going to take Fn and I'm going to add it with f of y because both of these are pointing in the same direction, which is up the y-axis. So once again, there's one vector, there's two vector, and there's three vectors. Okay, and we're going to subtract it from the f of gy that's pointing down along the y-axis. A y is equal to 0 because the box for these types of problem is not allowed to leave the surface of the ramp, which implies that it's just moving either up slope or down slope, but not to be flying away from the surface of the ramp. Okay. Therefore, to solve for f of n, I want to move this negative f g y to the right side, which makes it positive, and then I want to move this positive fy to the left, to the right side, which changes sign. That'll make it minus fy. But I know f of gy is mg cosine theta, and then fy is f sine theta. Just be careful with the thetas here because you got 20 and 30 degrees given. Well, f of gy is just mg cosine theta, m being 50, g being 9.8 cosine theta. Well, what's the theta here? Theta here is 20 degrees because this is f of gy. Minus 240 sine of 30. You notice I highlighted the angles here for you so that you don't get mixed up with theta and theta. Okay, if you need to, call it theta 1, call it theta 2, but here I know I'm referencing 20 and 30 degrees accordingly to based on how the arrows are drawn. All right. Now, if you simplify it, you should get a magnitude of 340.49 newtons. I hope that helps. Stay nerdy, don't be whack.